Here's our second example to show that question, so it's a little mini proof. See if you can use the derivative to get our derivative to look like that. First glance, it looks like, based on the way that the answer is written and what we have to start with, it seems like using the quotient rule would be a good starting point. See how you did? So there's our quotient rule. Then once we've simplified the top a little bit, we notice that there's an x in common in both of those terms. You could factor that x out of the top. Once that x is factored out of the top, you could simplify it. And we get what we were trying to show. So now if it has a maximum point at A, well, what do we have to do? We have to make our derivative equal to 0 and solve it. And how do we solve an equation when x is inside of a logarithm? Well, we get it to be a single log, and then we can change it to exponential form. So the base of natural log is e. Here the exponent would be a half equal to x. And since this question tells us it's a local maximum, we don't have to do the first derivative test to show that. Because it just asks for the x coordinate, we don't have to plug this back into the original function to try to find out what the y coordinate would have been. So the graph of this cubic function has a maximum point somewhere between x equals -1 and x equals 3. We could find the coordinates, but we're just going to find the x coordinate of this maximum point. So there's our derivative, which we can factor. Now, of course, again, it only tells us that there is a maximum between -1 and 3. 2/3 is the only one between those two values. So we know already that that is going to be our local maximum. But we could do the first derivative test to verify that. And I've showed that off to the side there. Typical of the IB, they have a question that has a constant as a variable inside of your function there. So p is a constant, so you can't just plug it right into your calculator and solve everything. This way they can add some non-calculator style questions on the calculator part of a test, but maybe later on in the question you need your calculator. But for this part, you'd have to show some stuff of what you know without your calculator. So we're going to find our derivative. And then it tells us there's a minimum value, and it says when it is. So now we have to work backwards and think about what does that mean and how we can find the value of p. So our derivative, I'd move that x up to the top. It's probably easier as a power rule than it is as a quotient rule. But either way, once you simplify it, you should get 2x minus p over x squared. So now if there's a minimum value at x equals -2, that means if you were solving the derivative, if you had made the derivative equal to 0 and you solved it, you would have got -2 as an answer. So what does that mean? Well, it means that when we make the derivative 0, we can plug in -2 because we knew that that was the answer that would give us 0. And now that we've done that, we have only p to solve for, and we can find that the value of p is negative 16.